Welcome to the Explainer. You know, string theory has this reputation for being, well, just bizarre. But what if I told you that its wildest features, like all those extra dimensions, aren't just random guesses? It turns out they're actually the result of some incredibly strict, unbreakable mathematical rules. And that's what we're diving into today.
All right, let's just get right to it. This is the big one, isn't it? Why on earth would physicists say our universe has 10 dimensions? I mean, come on. We see 3 dimensions of space, 1 of time, that's 4. Where are the other 6 hiding? It sounds totally nuts, like something out of science fiction, but you're about to see that it's anything but arbitrary.
And the reason is, well, surprisingly simple. It's not a choice, it's not a preference. The math literally demands it. You can think of the equations of string theory like a really, really delicate piece of machinery. For it to run smoothly and not just fall apart into nonsense, everything has to be just right. And the number of dimensions? That's probably the most famous and most important dial on that machine.
So let's dig into that. How can a bunch of math on a blackboard possibly tell us how many dimensions our universe should have? It all goes back to the very first version of string theory, and the simplest kind of string you can imagine.
Okay, so you're probably thinking the answer is 10, right? Well, not at first. The very first number that popped out of the equations was 26. Yep, 26. The original version, called bosonic string theory, came with this incredibly specific and frankly even weirder prediction.
So why 26? Well, it's all about balance. For the math to actually work, to not just break down and give you answers like infinity, it has to be perfectly self-consistent. It's almost like a cosmic balancing act. On one side of the scale, you've got the quantum jitters of the string itself. On the other side, you've got the number of dimensions it can jiggle around in. If those two things don't perfectly cancel each other out, the theory just breaks. And it turns out, for this simple string, that perfect balance, what they call the central charge, happens only, and I mean only, in 26 space-time dimensions. Any other number, and the whole thing falls apart.
But, okay, there is a gigantic problem with this theory. A pretty fundamental one, actually. This 26-dimensional universe, it's empty. It has force particles, like light. But it doesn't have any of the stuff that makes up, well, us. No electrons, no quarks, no matter. So as cool as it was, it just couldn't be the final story.
So physicists needed an upgrade, and that upgrade was called the superstring. The key new ingredient was something called supersymmetry, a really powerful idea that for our purposes let them finally put matter particles, the building blocks of everything, into the theory alongside the forces. And adding this one new thing, it completely changed that cosmic balancing act.
And this is just so cool, because when you add in supersymmetry to account for matter, you have to rebalance the whole equation. And when you do that, when you run the numbers again, out pops a new magic number, 10. This is where the famous 10 dimensions come from. It's the mathematical price you have to pay to have a theory that includes both matter and forces. It's not a choice, it's a consequence.
Okay, so now we've got our stage, right? A 10-dimensional spacetime. So, where are the actors? How do you take a single, tiny, vibrating loop of string and make it be a specific particle, like a photon or an electron or a quark?
The answer is this amazing mathematical tool called a vertex operator. Now, the best way to think about this is like a recipe or a blueprint. It's a very precise set of mathematical instructions that you basically poke the string with. And those instructions tell the string exactly how to vibrate to become, say, an electron, with the right mass, the right charge, the right spin, all of it.
Now, don't worry about trying to read these equations. You don't need to be a mathematician to get the big picture here. Just look. The formula on the left is for a closed loop of string, and the one on the right is for an open string, like a little shoelace. They're obviously different, right? That's the whole point. The recipe is super specific, not just for the particle you want to make, but even for the type of string you're using.
So here's the really crucial takeaway. Every single particle in the standard model, and any new ones we might find, has its own unique vertex operator, its own personal recipe. This is the dictionary. It's what translates the language of vibrating strings into the language of particles that we actually see in our experiments. All right, so we've got our stage, 10 dimensions. We've got our actors, the particles created by vertex operators. But a play isn't very interesting if the actors just stand there, right? The real story of physics is about interactions. So what happens when two strings meet? And this, for my money, is one of the most beautiful parts of the whole theory. See, in our old way of thinking, particles are just points.
And when they collide, it all happens at one single, infinitely sharp point in space and time. And that little point causes all sorts of mathematical nightmares. But strings are different. They're not points. So they don't collide, they merge. As you can see, two strings come in, they smoothly join up, and then they split apart again. The interaction isn't some extra rule you have to add, it's just part of the geometry of strings.
So if you're a physicist and you actually want to calculate what happens, how do you do it? Well, it's basically a three-step recipe. Step 1, you say what particles are coming into the interaction and what particles are coming out. Step 2, you stick the right recipe, the correct vertex operator, onto each of those strings. And then step 3, you do something that is just fundamental to all of quantum physics. You add up every single possible way that interaction could have happened.
Now that last step, summing over all possible ways, we really need to zoom in on that, because this is where the geometry of string theory just goes to a whole new level and gives us this absolutely mind-blowing picture of how the universe works.
So what does summing over all possibilities actually mean when you're talking about strings? It means you literally have to account for every possible shape the interaction surface could have made. So you calculate the chance it happened with a simple smooth surface, kind of like a sphere. But then you have to add in the possibility that the surface briefly formed a donut shape with one hole. And then you add in the possibility it formed a shape with two holes, and 3, and 4, and on to infinity. You have to sum up all these different shapes, or topologies, to get the right answer.
And you guessed it, this isn't an option. It's another one of those unbreakable rules. The core engine of the whole theory, something called the Polyakov path integral, basically acts as the master instruction book. And it says, flat out, you must sum over all these different topologies. It's not a suggestion, it's a requirement for the math to hold together.
Okay, so let's put it all together now. We've got the strings, we've got the particle blueprints, the vertex operators, and we've got this wild idea of summing over all possible shapes. When you combine all of that, you get one single master equation.
And there it is. Again, don't sweat the symbols. Just see the story it's telling us. See that big curvy E-looking thing? That's the sum over all the shapes, the sphere, the donut, the two-hole donut, all of them. And see that part with the V's? That's where you plug in the blueprints, the vertex operators for whatever particles you're smashing together. Literally, every idea we've talked about is sitting right there in this one beautiful expression.
Think about what that means. This one line of math is, in principle, the ultimate recipe book for particle physics. It gives you the complete set of instructions for calculating the probability of any interaction between any particles that the theory describes. I mean, the ambition of that is just staggering.
And that brings us to the biggest question of all. We've just walked through this incredibly elegant, powerful mathematical story. It's a story built on these rigid, unbreakable rules that seem to dictate everything from the dimensions of space-time to how particles talk to each other. It all hangs together perfectly. It's a beautiful story. But the one thing we still don't know for sure is if it's our story. Is this amazing math the actual description of our universe? That's the question that keeps physicists up at night.